But now GSM with Dieter Spaar.
Good evening. I'm a self-employed software developer, and one of my so-called hobby projects in the recent time was experimenting with GSM. One of the results of those experiments was implementing a denial of service attack to the GSM network in a mobile phone. Why experiment with GSM? The GSM system and its protocols, it's there for quite a long time. In Germany, the D1 and D2 net was available since 1992. However, GSM is not that well researched compared to, for example, TCP/IP. For TCP/IP, it's really simple. You just need two PCs with network cards, and you can start to play. You find endless client and server applications in source code. You can even have a look at the TCP/IP stack source code and start. For GSM, it's very different. Even if you buy a cheap phone, you don't have control over the network side. And even with these cheap phones, you normally don't know what is going on inside of the phone. However, the situation has changed in the last 1 or 2 years. Used equipment can be bought on eBay. You find GSM network equipment for a reasonable price. Then there are several open source projects which I will introduce later in more detail: OpenBTS, OpenBSC, and AirProbe. The specification for GSM is available. This is not the problem. However, it's really huge. The whole specification, including UMTS, is nearly 2,000 documents with partly more than 400 pages in single documents. If you want to start to understand it, I would recommend to read a book and not start with the specification. Use the specification as a reference. Good books usually refer directly to the specification so you can look up the details. Before I continue, I want to introduce just a few acronyms we need for this talk. It's not that complicated. The mobile station is how the phone is called in GSM terms, MS or mobile station. Then we have the BTS, it's the base transceiver station. This is what you actually see from the GSM network. Those are the antennas on the buildings and on the masts. Behind the base transceiver station is the BSC, the base station controller. It takes care of normally more than one base transceiver stations and controls them. We also have the mobile switching center, which is responsible for routing the calls inside the network or to the fixed telephone network. The visitor location register is a database of all the phones which are currently registered to the base station subsystem. The terms, we don't need them in this talk. But I just mentioned them. It's the home location register, which holds the information, basically what your operator knows about you and the phone and the SIM card and all that stuff. The authentication register, it's responsible for that you can use the network, that your SIM card can register on the network, and that you can make calls. The equipment identity register is a database of the phones, and it can be used to blacklist phones which are known to be stolen. Now a few more details about those open source projects. One of them is OpenBTS. As the name implies, it's about implementing the base transceiver station. The hardware of OpenBTS is based on the USRP, the Universal Software Radio Peripheral. This is open hardware. You get the diagrams, the schematics, which can be used to send and receive on a rather wide range of the spectrum, basically from DC up to several gigahertz. It all depends on the radio front ends you plug into the USRP. OpenBTS implements the air interface as a software-defined radio. This means all the signal processing, modulation, demodulation is done in software which runs on the PC. OpenBTS does not directly model this GSM architecture I've shown in the picture before. It uses a directly RAM to SIP approach. SIP is basically you get voice over IP afterwards, and it uses asterisk, an open source phone switch to make the calls into the network. The second project is OpenBSC. OpenBSC implements the base station controller. It implements the ABIS protocol, which is used to talk to the BTS, plus some parts of the mobile switching center and the home location register. OpenBSC currently supports two base transceiver stations. The first one is the Siemens BS11 micro BTS. It's an old device, about 10 years old, for GSM 900. The output power is 2 watts, but it can be reduced down to 30 milliwatt. The advantage of the BS11 is that it is cheap. However, also it's called micro BTS, it's quite heavy. You have 30 to 40 kilogram depending on the configuration. Configuration for the BS11 means it can have 1 or 2 transceivers, and if it has 2 transceivers, it's the heavy unit. The ABIS interface for the BS11 is an E1 interface. This is ISDN primary multiplex rate, so not the standard ISDN you usually have at home, but the more advanced one. The second base transceiver station supported by OpenBSC is the Nano BTS from IP Access. This is a rather current unit. It's available in several configurations and for several GSM bands. The output power of, for example, the 1800 megahertz device is 200 milliwatt. As you can see from this rather low power, the Nano BTS is intended for indoor installations and to cover holes where the coverage of the standard net is not that good. It's also used on airplanes and on ships where you usually don't have any GSM at all. The Nano BTS is also available with GPRS and Edge, although this is not yet supported by OpenBSC. However, work is in progress, and you probably can expect GPRS support in OpenBSC soon. Another big advantage of the Nano BTS is that you can plug it into normal network equipment. ABIS is implemented over IP, so no special interface card in a PC is necessary to talk to the Nano BTS. Just to get an impression, there's a picture of the Nano BTS on the left side and the BS11 on the right side. Those 3 little wings are the antenna of the Nano BTS. The black box on the right side is the antenna of BS11. And you see really the difference of the size. This BS11 is a full metal case, and that's why it is so heavy. And also inside, a lot of shielding, a lot of metal. You really get those 30 to 40 kilogram just from the metal. The last project I want to introduce is AirProbe. AirProbe is about passively sniffing the GSM air interface. Similar to OpenBTS, it's based on the USRP and GNU Radio. One of the goals of AirProbe is to analyze the air traffic and directly feed the results into Wireshark, the open source protocol analyzer. Wireshark already knows quite a lot of GSM protocols. However, hardware is missing to use it, for example, to sniff the air traffic. AirProbe can also be used for the upcoming A51 GSM encryption cracking project. Carsten Nohl this morning gave a really great talk about this already, so I don't mention any details here. I want to give a short overview about this DoS attack before I explain the details. The theory for this denial of service attack is known for quite a long time. However, so far, there are no practical demonstrations, or at least no implementation inside a phone which I'm aware of. The attack itself is possible because of the way the network works. When a phone wants to access the GSM network, it has to follow certain rules. I will explain the details later, but those rules are basically the reason why this DoS attack is possible. So you can't just change the rules and avoid this attack. This denial of service attack affects one cell. The cell you are attacking is affected, but not the whole network. The attack takes place in a very early stage. The phone has not authenticated to the network, so you can even perform it with a phone which has no SIM card inserted at all. Another advantage of this attack is that the phone has not yet transferred any information about itself to the network. So it's an absolutely anonymous attack. And as I already mentioned, not much can be done against it. The only thing you can do is try to locate this attacking mobile and get hold of the person who is performing this attack. But this can be difficult, especially imagine a crowded place somewhere in the city and there are lots of people who are using a phone. Tracking or finding one person with an attacking phone is really hard. And it takes some time, so you still have a certain time range to perform this attack and can be sure that no one will detect you. I now want to explain just a few details we need to know to understand this attack about the GSM network. GSM uses TDMA, time division multiple access. A data stream is, the data stream in this case is the physical channel, is divided into frames. Each frame has 8 slots and each user is assigned a slot. It's a bit more complicated in reality, but this is enough for our explanation. Inside those slots, the information, the data which are transferred in so-called bursts. In GSM, we have several different burst types. For example, there is the frequency correction burst. This burst is sent by the base transceiver station so that phones can synchronize on the frequency. The oscillator of a phone is usually not that accurate, so it has to, there has to be some way that it can synchronize to the exact frequency. This is the frequency correction burst is used for that. There's also the so-called synchronization burst. It fulfills a similar purpose. It is used to inform the phone about the timing information of those frames and of those time slots. Another burst, the burst we use in our attack, is the so-called random access channel burst, or RAC burst. This is the very first burst an idle phone sends to the network when it wants to access the network. Idle phone means the phone is receiving the network, it is synchronized to the network, but there is no active conversation between the phone and the network yet. The phone is not transmitting anything. This very first burst, which can be sent by the phone, is rather short. The reason is the mobile station does not know how far it is away from the base transceiver station. It sends it burst. This is here at the bottom. It sends it burst, the burst when it receives the beginning of a frame. Due to the propagation delay, this burst takes some time till it arrives at the BTS again. And as we can see from this diagram, the burst is somewhere inside of the slot. If the burst would be long and would have the length of the whole slot, it would overlap and we would disturb the information which might be transmitted in the slot which is coming afterwards. So this burst is really short, and we can only carry 8-bit of information and transmit 8-bit of information with this very first burst to the network. With 8-bit, you can't, of course, transmit information about who you are. You just say, I want to access the network for a certain reason. I want to make a call. I want to answer a call. I want to get a special channel, for example, for GPRS. But that's all. Nothing else is possible with this burst. What happens inside the network when this burst is received? This burst is called channel request. This is the channel request is sent with this WAC burst. The BTS receives it, and it asks the base station controller for a channel. The base station controller activates the channel, the activation is acknowledged, and then the base station controller forwards this assignment of a channel through the BTS to the mobile station. At that point, we have a running channel, and now the system, and now data can be transferred. However, in our DoS attack, we simply ignore this immediate assignment. We just send the channel request. So we allocate channels. Channels are a limited resource of the BTS. You usually have, let's say, between 20 and 40 channels in the, available in a normal-sized BTS. So what happens if we just allocate them? Usually this channel, or not usually, this channel is assigned a timeout. If the channel is not established within a certain amount of time, it will be released by the BSC again. This timeout depends on the manufacturer of the network equipment. It's in the range of 1 second to 5 seconds normally. You can send, if you continuously send those channel requests, you can send around 100, it depends on the configuration, to 200 channel request messages per second. You can imagine if you only have around, let's say, 40 channels, they are exhausted really soon. The effects of this continuously sending RAC bursts, with continuously, I mean you send the RAC bursts in every possible slot. Two different configurations are possible. One is you can send about 200 bursts per second. The other configuration is you can send 100 bursts. But this is really sending a burst in every possible position. When you do this, you first of all jam the signal of other phones. If you are very close to your BTS and you send a strong signal, the other phones don't have a chance to come through. You have the strongest signal, you win. The second effect is, of course, resource allocation. Those channels are exhausted rather quickly. This denial of service attack does not have an influence on already existing connections. If you're already making a phone call, it will not be disturbed, it will also not be disrupted. However, if you want to make a new call, if you want to register to the network, you turn the phone on and the phone wants to register to the network. If you are handed over from a different cell to this network, or if you want to answer a call which is intended for you, it can be impossible or really difficult for the phone to get access. As a consequence of this attack, the phone might switch to another cell, if there is a cell, with a better signal, but usually in crowded cities, the network planning is in a way that there are not that much alternatives for such a decision. This attack, however, is no 100% guarantee that a phone cannot access the network. So one application of this attack might be you want to make sure that, for example, a bomb in Iraq is not triggered by a phone call. Then you try to send those bursts and block the cell completely. It works if you are close to the cell and have the strongest signal, because then you jam also. But if you are too far away and want to make sure that you block the cell completely, you cannot trust on it. So for this application, this attack is not useful. However, one useful application is you can attack IMSI catchers. An IMSI catcher is basically also a base station. However, it's a false base station. It's intended to implement a man-in-the-middle attack by saying, hello, I'm a bus station, I have a stronger signal than the official cells, and the phones will take this stronger signal and try to register on this IMSI catcher. There are certain patterns which allow to detect that an IMSI catcher is trying to catch a phone. One of the obvious things for a phone is there is no encryption in use if an IMSI catcher wants to talk to a phone. So if the phone detects, okay, there seems to be an IMSI catcher in place and wants to get me, a modified phone software could ask the user, do you want to deny the IMSI catcher and send continuous rec bursts to him? This would surely work because usually this IMSI catcher is just a very small BTS. It cannot handle a lot of requests. If you apply this DoS attack to the IMSI catcher, it can no longer be used. I implemented the attack in a phone called the TSM30. This is a Spanish phone. It's about 6 years old. It supports GSM, GPRS, SWAP, no UMTS. The phone is based on a GSM chipset from Texas Instruments. The chipset is called Calypso. It consists of 3 chips. One is the main processing core, which contains an ARM and a DSP processor. And then there are 2 supporting chips. One is for the digital baseband, the other is basically the RF transceiver. The firmware for this phone can be found. You just have to search for it, you will find it. To give you an impression of the complexity of such a phone firmware, the complete source code for the Calypso ARM, just the ARM processor, is about 2.5 million lines of code. From this 2.5 million lines of code, the GSM protocol stack is about 400,000 lines of code, and layer 1 is 130,000 lines of code. Layer 1 means this is the interface between the GSM protocol stack to the actual radio hardware. Just for completeness, there's also a second microcontroller inside this phone with 350,000 lines of code, but it's not for GSM-related operations. It controls the camera which the phone has, the USB port, and the micro SD card slot. The attack code itself, it's just a few lines of code. The problem is to find the right place. You have to spend, let's say, a few weeks if you look at this code, try to understand it, but then you find or get an impression what can be done with it, and yeah, you can start an experiment. In this diagram was extracted from data retrieved from a protocol analyzer on the ABIS interface. ABIS interface, this is the interface between the BTS and the base station controller. The lower diagram shows the number of RUC bursts generated over time. In the upper diagram, we see the number of channels which were allocated by those RUC bursts. This experiment was done with a real GSM network equipment, but in a lab environment. So there was no harm done to any public operation of an operator. This BTS in this diagram had 2 transceivers, and it was configured to have at most 24 channels. We can see in the upper diagram that these 24 channels are allocated rather fast. What was interesting in this experiment was that not each channel has his own timer to check for the expiration, but instead this base station controller periodically checks if channels have expired and releases them all at once. those are those drops in the diagram. At every drop, the base station controller checks, are there any channels who have expired? Let's free them. In the next diagram, it's rather similar, but a different BTS, in this case 4TRX, 40 channels available. I have in this diagram, I tried to show how it would look like with 100% rack density. At the time this measurement was made, the implementation was not that perfect as it is now. Not that perfect means the phone was at that time not able to send a rack burst at every possible slot, but only instead about every fifth slot of what is possible. So in reality, it would most certainly look like the red lines. The number of channels which are released when the base station controller checks for released channels would be larger because a lot more channels have been allocated before, and of course the rate how those channels are reallocated again is much faster. From this diagram, we can see one thing. If we are not jamming, in the case of not jamming, another phone would only have a chance to get a channel in those places where the drops happen. If you look at the red lines, you can see that this error is most certainly rather small compared to the length where all the channels are allocated. So if several phones try to get access in a large cell, they have the chance to get through, but only if they are exactly at that time where channels are already dropped. To give you an impression how it looks like, I will show you a demonstration with OpenBSC. In this setup, we have nano BTS as the BTS. This is the unit here. It's connected to a laptop which runs OpenBSC. We have the TSM30, the attacking phone, and we have a second phone which just tries to get access to the network. This is the screen from OpenBSC and its output. You don't have to understand the details, just to show you what has happened. The first thing which has happened before when I turned it on was that the phone which does not perform the attack has performed his location update. It has registered to the network. If I now send an SMS, sorry, 1 moment. We see here the phone is connecting and it has sent an SMS. I get here the warning, the number is not in use. In fact, I dialed a number which is not known. There is, of course, no other phone which can answer. But here you see the text I've typed here, just hi, because it was easy to just press a certain key 4 times and you get hi from the word suggestion. So we can also show with this radio, you can hear actually how it sounds when the phone is sending. The sending phone interferes with the radio and you hear a certain noise. I will turn on the radio. Okay, the problem is our BTS is of course also sending. So if I go closer to it, you hear the noise is getting louder. I try to resend the SMS. You have heard it, signal? Okay, I repeat it. Go to the microphone here. Okay. What is happening? Okay, I think I was, let's try it again just to be sure that we really hear this signal. I think I'm not close enough now. It worked before, but now? The last try, okay. We see on the screen that we actually connected, but hearing it can be interesting, of course. Do you want to try it?
Yes.
Maybe it's the microphone, I'm not sure. Müsste aber schon.
Okay. Used to work is highly professional level.
We saw them, we see that the SMS is received, however, we don't hear it anymore. Okay, let's start the attack and maybe try it. Okay, I will now start the attack. In this case, the modification is done by dialing a special number. If the special number is dialed, the phone will start to continuously send rock bursts for 60 seconds and then stop again. I will start here. And you see the bursts are in the log, and now I try to get access. The colored lines are here are the release messages from OpenBSC when it releases the allocated channels. Those lines just mean we have released something. Usually, we have to see message sending failed again. If we would get access, we would see yellow, green, white lines similar to before. Can you hear this one? No, it does not work, okay. It does not work anymore. Of course, the power of the phones are adjusted to send in with a rather low level. Just in case, I have not mentioned it, we have an official test license to do this experiment. Thanks to the organizers of DeepSec, they managed to get a test license. So what we are doing here for this experiment is perfectly legal in this case. It's finished, the channels are released, and if I try to send the SMS, of course it works again. I don't know if any one of you tried to see this network. If the phone behaves well, you should not be able to see it, simply because our setup is in a way, the cell is in a so-called status barred. This is a flag which the cell transmits to the phones, and it tells them, you cannot use them. I'm a cell which is for testing purpose or other purpose, but not for normal operation. However, the old Nokia has a network monitor which allows to use just test cells and not regular ones. So Nokia phone is switched to reverse. It uses test cells instead of the normal network. Of course, the same thing with the TSM30. It's modified in the same way. We just did it to avoid any influence or interference with the phones of the audience. But if for some reason, I don't know how much time we have, if someone is interested, we can switch the cell and your phones would see the network. You can, of course, try to register. I can start the attack. Don't know.
Let's do it.
Okay, let's reconfigure the cell. I have to stop. So OpenBSC starting up again. Those messages are now the configuration messages when OpenBSC configures the BTS. Now this cell should be visible to the public. So if you do a manual network search with your phone, you should see ASA 00101 or testnet. This, someone already registered? Okay. Testnet or 00101. It depends on the software on the phone, what name it displays for this special network. I just have to turn on the attacking phone again. As you can see, several messages from phones which are registering. The yellow message location update request is the message which tells there's a phone. Okay, I see someone is trying to make a phone call. But of course, it does not work. We don't have configured this. You see it? It's just let me see.
Yes, yes.
Yes, of course, yeah. Okay, I see those error messages are actually happening if someone tries to make a phone call. The OpenBSC software will try to take this phone call, but there's actually no partner to connect to. So after a certain time, the channel will be reallocated, and those are those error messages. I'm just trying to, okay, my phone has registered again. If I now start the attack, it's now a different type of attack. I send different reasons why I want to access the network. One is I want to do a location update, so I want to register too, and the other is I want to get a channel for sending an SMS. But if the attack is running, normally no other phone should come through. Okay, I think it will take 30 or 40 seconds, then the attack is over again. The blue messages are just the error message, and which you see in between, but no actual connections, just error messages from something which happened before. We should see white, green, or yellow messages for a real connection. Okay, it's done. Now it takes some time to free the chance. We see phones can get access again. Okay, here are some links to the projects I mentioned before, to the places where you get the specification. And a special thank to Harald Welte and David Burgess. Those are the people behind OpenBSC and OpenBTS. They also gave this great GSM workshop here at DeepSec. And if you have feedback, there's also my email address. Any questions?
I have read the logs correctly that the IMEI number of the phone making the attack is locked, so that it's possible to determine who is attacking the network?
Yes, in our case, when a phone does a location update request, we can request certain information from the phone. We can ask the phone for the IMSI, for the EMAI, and this is what OpenBSC does in this case.
So if I have such a modified phone and like to have a quiet network during a speech, it would be an illegal attack to use this phone to cut out our other phones in the network.
You can block them that they get access, but you cannot disrupt the existing talk.
It's
Okay,
only during the speech, so that no telephone in the
Okay,
room can calls in.
Okay, but in this case, I would need more than one phone. We have, I think we have 3 providers, network providers here in Austria.
Okay.
I would need at least 3 phones to attack 3 different cells from the 3 different providers. And additionally, I'm not sure how the situation here is, but it could be that the phone in front of here is registered to a cell which is on the right side, and the phone back there is registered to a cell on the left side. So we might have more than one cell from one provider which is used to register the phone.
In my case, it would be enough if it switched off all the students during the lecture. That would be fine. Yeah,
You can do it, but I think it's really a legal problem, a serious legal problem, because you also block, of course, emergency calls.
I just wanted to make a short comment about the IMEIs that you've been seeing. You do not see the IMEI of the attacker, right? Just to want to make that clear. Because the IMEI can only be inquired after the channel has been established, but because we never fully established the channel, you never know the identity of the attacking phone.
In fact, this phone, the attacking phone, has not sent anything. It did not even have sent the location update. Of course, in this case, I wanted to turn it off, but the version of the software which can be found on the internet has a bug. It does not work all the time, the location update. So no need to turn it off. It's already turned off.
So something else that I think is kind of missed in that question is that when you operate this attack, you're not jamming the phones around the attack phone. What you are jamming is the serving cell. You're jamming service for the whole neighborhood.
Yeah, of course.
Not just the room.
Yeah.
You're shutting down. You're shutting down a whole neighborhood when you do this. You're not just jamming the room. You're not jamming phones. You're jamming the network.
Does it affect the other networks? Okay, I'm jamming the network. Yeah.
Yeah. I mean, and you. It's clear from your talk, but I think the way the question.
Okay,
I think the question kind of misses that point. That we're not talking about jamming an area around a room.
Okay.
We're talking about jamming the cell. That's a big difference.
We have time for a few more questions, so get them in now. Oh, didn't see.
The usual question, defense. Is there any way how a network could defend itself against such an attack?
The network, the network has to change the way how the network works. This is the problem. So you have millions, if not billions, of phones around which conform to this old GSM specification, and you either change the way the network works and say, okay, all those phones are can no longer access, or you don't, and then you have the problem that this attack is still possible.
And
of course.
Let them run around in the town, you can...
Yes, of course, it's simply scalable.
Serious damage.
It's simply scalable. And of course, the power consumption is not that high. In fact, it's even lower than doing a normal speech call. So if the battery is full, you can really do this attack a long time. And you just put it in your pocket and go around. No big equipment which might be necessary to go around and which makes it clear that someone is going on.
Any more questions? Next question, all right.
How hard is it to pinpoint the attacking phone using radio equipment?
One problem with detecting is that you send bursts, small bursts. Regular bursts, but small bursts. So standard equipment, for standard equipment triangulate your position, it might be hard. But I think David is the expert for this question. If you want to answer it.
Wait, just a second. Everyone needs to hear it.
With the typical type of radio location equipment used by civilian authorities, it would be extremely difficult to locate this phone. The amount of power that's being used to do this is very small, and the duty cycle is very low. These are short bursts, and the duty cycle on the channel is really low, so the total amount of power is really, really small. I mean, there's equipment, but your local civilian people aren't going to have it.
Yeah, sorry. Yeah, your comment first. Well, anyway, I just wanted to say, well.
Well, my only comment was you could light these things off and just leave them. You know, get a bag of them and just set them up all over the place.
Yeah, that was also my comment, because you said it's hard to locate the person who has that phone. I mean, if you just, it's cheap old phones, right? And in theory, I mean, technically, you can do this to any phone. It's just that you don't have the source code to the phone. But
Yes.
somebody who has access to that technology, has access to that information, it's very easy to make hundreds or thousands of these phones, and you just randomly distribute them. You put them in a package, and it gets shipped around with the postal services or whatever. I mean,
If someone wants to spend a lot of effort in terms of spending more time than just implementing it in an existing firmware, it's of course this Calypso chipset is used for different phones. Usually, this Calypso chipset is from Texas Instruments. Usually, they provide the GSM protocol stack from the same vendor. So phones working with the Calypso chipset have a high chance of using a similar in the terms of GSM stack layer 1 code software. And even if you only have the binary and you are an experienced reverse engineer, you can have a look how it looks in the implementation of the TSM30 and search for this pattern. And you will most certainly find it. Of course, the effort is much higher, but it would be possible with effort, let's say 2 months, for a very experienced engineer to modify a binary from a different phone based on the Calypso, based on the same GSM protocol stack, and based on same layer 1.
one more comment. I mean, I don't know how many of you know, but the iPhone jailbreaking, for example, works by exploiting the very same baseband processor that can do these kind of things. So you could imagine things like exploiting iPhones remotely and turning them into RATch bombs. I mean, it's technically not impossible, right? It can be done. If anyone wants to do that, there's nothing that prevents you from doing that.
Of course, the iPhone is not the same as the Calypso, but for an engineer who knows, let's say he was employed when developing the iPhone stack, and he knows where to look for, and he gives people some hint, it would be possible, because the iPhone baseband stack, this is where all this happens, is already exploited. This is, as Harald mentioned it, this is how the way jailbreaking for the iPhone works. It's not the application processor, it's the baseband processor, where all GSM operations are being performed.
When are you offering the workshop? Where and when?
I don't think I have to offer a workshop. A great workshop was already, has taken place here already.
Yes, that workshop is done. So everyone who didn't participate missed it. So I think you should think about when and where to offer the next workshop.
If Harald and
This
David
is actually
are
for your
contributing, of
questions
course.
too. So, anyone? How much is a phone like this?
How much? The price? If you get a used one on eBay, you have to look at eBay Spain. It's difficult because of the 6 years when this phone was distributed, but usually, let's say, €10 and €5 shipping to Germany, something like that. I even bought 2 brand new ones from, they were lying around somewhere and no one was interested in them anymore, €35 for 2 of them, brand new. Of course, for someone who really wants to do bad things, I'm rather sure that hundreds or more of those phones are probably not available. Maybe someone has them, but I have never seen them or offered anywhere. So it's something to play with. This attack is basically, it was a result of experimenting. You can also do other fancy things. As I mentioned, why not modify the firmware to detect IMSI catches and then display a warning? Or do some other things and try it out. This is researching in the GSM field. You can use this phone for this purpose. And it's one of the only sources for the GSM phone side in the moment.
Any more questions? Who's the guy who bought all those phones? And will he bring them to the workshop?
Those are not GSM 30. Very different ones.
Last talk, last questions. Well, if nobody can think of a good question right now, but would try to get an answer for later, you will be at the Meta Lab tonight?
Yes.
Great. So then, bring your phone.
No, I
and a
don't
soldering
think so.
iron. Exactly.
Of course, if there are some providers who would be interested to test it in a lab environment, surely possible. But I'm 100% not giving a demonstration on the official network. I even haven't tested it on the official network. Developing this attack, all what was used was the Nano BTS and the BS11. If you can connect the phone even with an attenuator and a cable to those base stations, and then you make sure that you really radiate nothing. So this can be used to test it and develop it.
So if there are really no further question right now, then I would like to thank Dieter Spaar for his talk. Thank you very much. Right, after this, of a short break, we will have the closing